Every neural network diagram you've ever seen, the circles, the arrows, the layers, looks complicated. It's really not. The whole thing collapses into one idea you already understand. That's what this video is. By end of the next 10 minutes, you'll be able to explain a neural network to anyone. Not a black box that learns from data, the actual mechanisms. Neurons, weights, layers, the forward pass, we'll cover all four. No calculus, no algebra, just the thing itself. Here's how most people picture a neural network. They imagine a digital brain, little virtual neurons sparking like a biology, somehow thinking. The image is exactly wrong, and it's why the concept stays confusing. A neural network is not a simulation of a brain. It borrowed the word neuron in the 1940s, and the metaphor stuck around long after it stopped being useful. What it actually is a stack of very simple math operations wired together so that every error from one layer informs the next round of adjustments. That's it. Let's build that from scratch. Start with one neuron, not a brain cell, just a box. Three things go into this box. Call them inputs. Maybe pixel brightness values from an image, maybe words from a sentence. Doesn't matter. They are just numbers. Think of weight as a volume knob. If a weight is high, that input matters a lot. If a weight is near zero, barely registers. The neuron multiplies each input by its weight, adds them all together, and then decides do I fire or not? That decision, fire or not, is called activation. If the sum is high enough, the neuron activates, passes a signal forward. If not, it stays quiet. That's the entire job of one neuron. Multiply, sum, activate. Multiply, sum, activate. Everything else in deep learning is just doing the same operation millions of times. One neuron can answer only one dimensional questions. Is this input high enough? Sure. Does this image contain a cat? Absolutely not. So we use many neurons arranged in a layer. Each neuron in that layer is paying attention to a different combination of the inputs. One might be detecting a horizontal edge, another a diagonal, another a specific whiteness gradient. None of them know about the cat set. They are just pattern detectors. Now a stack second layer behind the first. That second layer neurons receive the output of the first layer as their inputs. So now they are detecting a pattern of patterns, edges combining into shapes, shapes combining into features, features combining into a cat. That's the power of depth. Each layer handles a higher level of abstraction than the one before it. Deep learning just means more layers. That's what that word deep means. Nothing mystical. Here's the question that should be bothering you by now. Who sets a weight? If the weights are volume knobs, if they determine which inputs each neuron cares about, who's turning them? Initially, nobody. The weights start as a random numbers. You feed the network its first training example, an image of cat labeled cat. The network outputs dog. That's wrong. So the training process measures how wrong. And then it works backwards layer by layer, nudging each weight slightly in the direction that would have made the answer less wrong. Do that for 100,000 cat images, then a million, then 10 million. Each time a tiny adjustment to its own weight. By the end, the weight encodes everything the network learned and about what makes a cat look like a cat. Those weights are the models. When people say download a model, they are literally downloading a file full of this adjusted numbers. That's it. That's what the training produces. So let's close the loop. A neural network is a stack of layers, each made of neurons, each doing simple weighted sums where the weights are gradually adjusted by measuring and correcting errors across thousands of training examples. That's it. Not a brain, not magic, not just something that understands. A function with a lot of tunable numbers, tuned by showing it a lot of examples of what we wanted to get it right.